Thanks everyone for joining us today. This is Cybersecurity Safety and Equipment Protection Systems in Mining. We have with us today is Andrew Ginter, who's going to discuss some of the ins and outs about the cyber protecting of mining and metals, in this case mining. It's a very interesting topic. I was talking about Andrew earlier in the week, so can't wait to see what he has to say about it for everyone. Andrew, take it away. We don't hear you.
Thank you very much. And I hope I don't disappoint. Yeah, we're going to be talking about cybersecurity and how it's relevant to safety critical systems, to equipment critical systems in metals and mining. As we all know, mining is a very safety intensive operation. There are very large machines involved. Sometimes we have large numbers of people deep underground. There's airflow safety systems. There's toxicology and methane buildup detection systems. There's it's a sensitive environment, and the problem is that increasingly cyber threats are threats to safety and to the possibility of damaging very expensive, very long lead time equipment in these very sensitive, very big, as a rule, operations. So let's look at that. Let's look first at the threat. I've got a few slides on threat. Recent incidents, high-profile incidents in metals and mining. I live in Canada. Just north of me, the Copper Mountain mine, copper mine, was down for, I think, 6 days a couple of years ago because of a ransomware attack. Large financial impact. I'm not even sure how to pronounce it properly. Orbis Copper Recycling is a copper recycling business headquartered in Europe with facilities in many countries. A number of those facilities went down again because of a ransomware attack. Khuzestan Steel in Iran, there was, in roughly the same time, hacktivists targeted 3 steel businesses in Iran. And this is the one that went down. There was a fire at the site. Okay, the cyber attack caused a fire. Fortunately, there were no injuries. There was equipment damage reported, and the site was down for an undisclosed period of time. So these were examples in the news of why we're worried about cyber attacks on mines. A second thing to keep in mind, I'm going to talk about Volt Typhoon in a moment. Volt Typhoon was a nation state attack. It was attributed to Chinese intelligence agencies. When we're talking mines, the biggest mines are nation state targets. The biggest mines are geopolitically strategic assets. In the brain blank, in battery manufacturing, green energy, lithium is critical, and China controls most of the world's lithium production, and if not production, then processing, primary processing. Copper is emerging as a critical mineral because of global warming and everything going green and everything going electrical. When we have nations that are trying to control the supply, trying to dominate a particular branch of metals or ore production, we have nation state tampering with each other's mines. And the problem with this is that nation states are extremely capable adversaries. They have, in practical senses, almost unlimited talent, PhDs they can throw at the problem, time they can throw at the problem, money they can throw at the problem. And so if we are trying to prevent that grade of adversary coming in and messing with our safety systems, That's quite the challenge, and we're going to talk in a moment about how to rise to that challenge. But evidence, of this very recently, this is like a couple of months ago. Volt Typhoon was an alert put out by American authorities saying, "Look, Chinese intelligence agencies have broken into utilities, power utilities, water utilities, not mining, but this is an example of the behavior of nation states. Broke into the IT networks." And what did they do? Well, they did what's called living off the land, which means they got in through a phishing attack that click on a malicious attachment, or steal a password and log in with stolen credentials, or exploit a vulnerability on an internet-facing service that hasn't yet been patched. Use the window between the announcement and the patch to get in. Once you're in, they erase all evidence that they're in there. And they persist. Now they look like any other user. If you run an antivirus scan on the machine, you find nothing. There's nothing there. They are using the tools. I mean, Windows is a powerful operating system. Linux is a powerful operating system. Most of us use Windows in our automation. Those of us who don't tend to be migrating towards Linux. You don't need malware in these operating systems for an adversary to take remote control and keep remote control. And so they don't have malware. So you run an antivirus scan, you get nothing. You look at network intrusion detection scans, you get nothing, because these people are maintaining their presence in the machine. They have control of the compromised machine, but they're not doing anything with it. There's nothing suspicious that they're doing. They occasionally, the forensic record, these people have been, in these targets for between 6 months, 12 months, sometimes longer. They've been in these targets for a long time. The forensic record, when you look really hard at it, it looks like they occasionally dip their toes into the OT network, apparently just to prove they can do it, and then they pull back. They don't do any damage. The intelligence agencies have analyzed this and said, why would an adversary do this? There's no ransom demand. There's no monetary advantage. There's no sabotage. There's no damage. The only reason that makes any sense is that they are maintaining the ability to cause damage in the future. So you've got a nation state causing damage, with the ability to cause damage in the future, using an attack technique that is extremely difficult to detect because there's nothing they're doing that's suspicious. So this is the world we're up against. Living off the land techniques, nation states acting against each other in a context, of ransomware and hacktivists actively trying to cause damage and steal money and so on. This is the world we live in. Bigger picture. This is from the Waterfall 2024 threat report. The threat report, it's arguably the most cautious threat report in the industry. I recommend it to everyone listening. We've tracked over time, we counted cyber attacks. We count cyber attacks that are deliberate attacks, not equipment failures, not errors and omissions. Deliberate attacks with physical consequences in heavy industry and critical infrastructure and manufacturing, including, of course, mining and metals, in the public record. No private disclosures. The entire data set is in the appendix. If you download the PDF and you want to check any of the events that we've counted, you can click on the link. You can go to the front page of the New York Times and see for yourself if it was worth counting. We've been counting these things since 2010. In 2010, there was one attack that met that criteria. It was Stuxnet. In 2011, there was none. There was lots of attacks, but none of them caused physical consequences. They were stealing information. The whole decade, 2010 through 2019, that decade bounced around between 0 events and 5 events in the year, attacks. And then it changed. This decade, 2019, there was 6 events. 2020, there was 18 attacks. The next year, there was 23. The next year, there was 57. Last year, there was 68. 68 attacks that took down or otherwise physically impacted over 500 sites. Most of these attacks impact multiple sites. this decade, we've gone from sort of a theoretical problem last decade to a problem this year or this decade that appears to be growing exponentially, a little bit less than 2 times growth per year averaged over the 5 years. Most of this is ransomware. Some of it is hacktivists. The fraction that is hacktivists is growing faster than the upward curve of all the events. Hacktivist activity as a fraction of what we're seeing is increasing. This is important because, you know, ransomware tends to want to extract money. If they do damage to a site, if they shut down production, in our analysis, it does not look like ransomware is deliberately trying to do this. These are sort of unanticipated consequences. Hacktivists are deliberately trying to shut us down. Hacktivists are looking for all the press they can get. The bigger the site they can shut down. Hacktivists deliberately target critical infrastructure. Now, ransomware, the tactics are evolving. Ransomware does target critical infrastructure with the goal of shutting it down in hospitals. Ransomware targets hospitals deliberately, systematically. Nation state activity is on the increase, but it's still comparatively small numbers. This is the world we live in. And, you know, we're seeing roughly doubling every year, a few more doublings, and these are going to be very large numbers. And, you know, we might say, well, today ransomware doesn't seem to be deliberately taking us down. Well, they're deliberately taking down hospitals. Who knows what the tactics are going to be in the future? The motives of these attackers can change much more quickly than their capabilities. Capabilities evolve very slowly. We can model capabilities, you know, fairly accurately by watching what's happening on the internet. Intent can change in a heartbeat. A hacktivist can be watching a news report and from literally one heartbeat to another, get mad at what they see in the news report and decide to attack a new target. Intent is very difficult to predict. Capabilities are easier to predict. And the problem is that a lot of the ransomware and a lot of the nation states have the same capabilities today. Intelligence agencies are reporting that the richest ransomware actors are buying and selling attack tools to and from nation states. The high end of ransomware and nation state attacks are using the same attack tools and technology. This is sort of a black market that's emerged. Ransomware targets everybody with money with nation state grade attack tools and techniques. And nation states are targeting the largest mining sites. That's the world we live in. How does it work? How do these attacks work? The key word here is pivoting. I'm just going to go through this briefly, but basically the bad guys get a foothold in the IT network, in the enterprise network. They take over a machine and either sit on it, the way Volt Typhoon did, or more commonly, use the remote, use remote control of that compromised machine, use that compromised machine to figure out what's going on in the network and attack other machines. It's called pivoting an attack from one machine to another machine. And having taken over that other machine, they look around its network and pivot further. They can pivot through firewalls. They can pivot into safety systems. It's only been done a couple of times, but it can be done. It has been done. Any system that can be reached by pivoting through one system and attacking the next, even through firewalls, is at risk of this kind of attack. You can even pivot through the cloud, go from the internet, compromise a cloud, and pivot through the cloud, use the compromised cloud to attack everything that the cloud is connected to back in our industrial sites. This is the world we live in. This is the modern attack, is pivoting. People ask sometimes, is it really credible that you can pivot through a firewall? The answer is yes. Is there a firewall between anybody's enterprise network and the internet? Of course there is. There's always a firewall between the enterprise network and the internet. Ransomware routinely breaks into enterprise networks, don't they? Thousands of incidents last year. Yeah. Every one of those attacks came through the firewall, breached the enterprise to IT firewall. If they can get through one firewall, they can get through the next. There's evidence of this. I've got an older white paper on the Waterfall website, 13 ways to break a firewall. It's the depressing thing is that there's lots of new ways to break a firewall, and all the old ways still work. So this is the world we live in. Pivoting is the nation state style of attack that comes in over the network, and it's very effective. That's the bad news. The good news, how are we going to defend minds against that threat environment? The good news is something called cyber-informed engineering. This is an initiative that the Department of Energy is funding at Idaho National Laboratory in the United States. I recommend it highly. It is a little bit energy centric. It's focused on oil and gas and electric energy sources. Not so much mining, but the principles are pretty much universal. And everyone who's read the thing has figured this out. And is using this cross industry. And I'm one of the voices in the community. Lots of people are going to the funding agency saying, can you broaden the scope of this a little, because this is really useful and it's broadly useful. But the point is that it's available. What is it? Well, it's written by PhDs. The artifacts that have come out so far are a little hard to read, but sort of informally, it's modeled as a coin with two sides. One side of the coin is cybersecurity. Teach engineering teams about cybersecurity. Teach engineering teams about cyber threats, because it's the engineering teams that are responsible for designing the systems that control the physical world and addressing threats to those systems, be those threats components wearing out or cyber attacks. So teach the engineering teams about cyber attacks. Nothing new there. We've been singing that song for 20 years. The other side of the coin is engineering. What does that mean? In a mine, you climb into an elevator and you go down 1.5 kilometers underground. There's 25 of you miners in the elevator going down. If a cyber attack takes over the computer, the programmable logic controller, the PLC controlling the engine on the elevator, you could go down much faster than you're supposed to. You could hit the bottom hard. How would you like to, this is your life on the line. Imagine every one of us, we're going down the elevator, our life is on the line. How would we like to be protected from that cyber attack that that runs the engine on the elevator too fast? How would we like to be protected? Would we prefer a mechanical centrifugal brake, where if it's a wheel against the side of the wall that as we're going by, the wheel is turning. If the wheel turns too quickly, the centrifugal force forces a switch against an electrical contact, and that electrical contact cuts power to the engine and cuts power to a lock suppression system. The lock mechanically engages, the elevator stops, and we get rescued. That's how it works. There's no computers involved there. Would we prefer that centrifugal safety, or would we prefer a longer password on the PLC controlling the engine? The gurus that I asked this question, the obvious answer is I'd like the electromechanical device. Thank you. It's unhackable. Even if I hack the computer on the engine, this is going to save my life. The true gurus say, Andrew, you're being deceptive. You're trying to deceive us. You're asking us the wrong question. And they're right. I am trying to deceive us. Cyber-informed engineering is positioned as a coin with two sides. When you spend a coin, do you choose which side of the coin you spend? No, you spend the whole coin. The gurus tell me, Andrew, if my life is on the line, I want the centrifugal governor. I want 4 of them because these are mechanical, they wear out. And I want a longer password on the PLC. And I want a boatload of cybersecurity beside that. And that's CIE. That's the right answer. When we spend that coin, we spend the whole coin. We spend the cybersecurity, we spend the engineering. I'm going to focus on the engineering side of the coin, not because it's more important than cybersecurity. We need it all. I'm going to focus on the engineering side because that side has been neglected historically, and that is a piece of the puzzle, a powerful. It's a bunch of powerful tools that we need to become more aware of. We need to use more routinely. Examples of tools like that: overpressure release valves for pressure vessels, boilers, or catalytic crackers. Think about it though. Where is the electromechanical, the centrifugal governor? Where is the overspeed governor in ISO 27001? Not a hint of it. Where is it in the NIST cybersecurity framework? Not a word of it. Where's overpressure relief valves in the industrial 62443 standard? Not a hint of them. These standards are cybersecurity. They apply to the cybersecurity side of the coin. They say not a word about the engineering side. The engineering side, these are powerful tools. Engineers have been focused on protecting worker safety and protecting public safety for 100 years. And they've developed powerful electromechanical tools, safety systems, that just work and can't be hacked. And we need to start, we do use these systems routinely. Engineers use these systems routinely to address physical threats. What happens if there's an earthquake and we have people trapped underground? They have physical designs to address that possibility. What happens if there's a hurricane comes through? They have physical safeties to address that possibility and protect worker safety in that context. What happens if a cyber attack comes in and takes out all of our safety instrumented systems? That's a new risk. That's something that the engineering profession needs to wrap their heads around and start using these powerful tools to address not just the risk of earthquakes and the risk of tornadoes and the risk of hurricanes, but also the risk of a cyber attack. Cyber-informed engineering talks about cybersecurity mitigations and engineering grade mitigations. What's engineering grade? Engineering grade is unhackable. It is deterministic. It behaves the same way all the time with mathematically, modelable failure curves. That's an engineering grade solution. And there's expectations when we deploy solutions to protect workers, to protect the public. The expectation, when engineers design a bridge, what's the expectation? We expect that bridge to carry a specified load in a specified operating environment for a specified number of decades with a large margin for error. That's what we expect. When we have safety critical automation, our workers and the public and the government, the society expects that our designs, our automation designs, will stand up, will carry, will support a defined threat load until at least the next opportunity to upgrade our systems. And we know that these upgrade opportunities occur at long intervals in the mining industry. So we need, to carry a specified threat load reliably for a long period of time with a large margin for error. How large a margin? Well, I spoke to somebody who designs pedestrian bridges. I pointed at a pedestrian bridge. I said, how do you know how much load that bridge has to carry? He says, oh, that's easy, Andrew. He says, there's barriers on both sides of the bridge. You cannot drive a vehicle onto the bridge. The only thing the bridge can carry is people, or people and their pets, animals. People, as a rule, are less than 2 meters tall, and as a rule, they're made of water. So you model 2 meters of water, the width of the bridge, the length of the bridge. That's the maximum load. That's what you have to design the bridge to carry, he says. And then you take that number and you multiply it by 8, because these are people. Failure of the bridge under load is unacceptable. Same thing with mining elevators. The average mining elevator can carry 25, 50 people. It's a metal cage. It's got weight. You've got a cable carrying the weight of the elevator and the load, the people. And that cable, as a rule, is rated for twice the maximum load, twice the weight of the elevator plus all the people in it. And the average elevator has 6 of those cables. So they're rated for 12 times the load because failure of the device under load is unacceptable. This is the expectation for designing safety systems, for designing cyber protections for safety systems when human life and public safety are at risk. And so cyber-informed engineering is not just about these mitigations, it's also about the perspective, about the engineering perspective on risk. And when we do risk assessments, what we find is that too often there are blind spots. We look at our mining systems and we say, oh, what if the bad guys get in and we have to shut the mine down? That's not the biggest risk. The biggest risk is that the pivoting attack reaches the safety systems, compromises the safety systems, causes an unsafe condition, and now the safety systems don't save us and we fail and people die bluntly. That's the worst case outcome. And even if we wrap our heads around that, a lot of us are blind to the fact that cyber attacks can also damage very expensive, very long lead time to repair equipment. Large engines, like the engines taking these elevators down the shaft, the largest engines, if we're in a mine that's on the grid, now not all our mines are on the power grid, but some of them are. If we're on the grid and you disconnect the engine, that the computer controlling the engine turns off power to the engine for a fraction of a second and turns it back on again, what happens? The engine shifts out of phase with the power grid. When you reconnect, there's a conflict. The engine needs to be in a certain piece of its rotating to match the power grid. There's a conflict, there's a fight, there's a battle. Who wins? The power grid always wins. The engine is forced, very quickly into the proper position. The force, the torque on the engine is enormous. You risk destroying the engine in an attack like that. Protective relays are supposed to prevent that kind of attack. And they're entirely software. They can be misconfigured. You can connect to them. You can pivot into them. You can download new firmware into them if you compromise them, if you exploit a vulnerability. And it's possible. And a lot of us are saying, oh, just like safety systems protect human life, protective relays protect the equipment. Yeah, but they're both software. And if we have no electromechanical safeties in there, we risk compromising all that software in a cyber attack. Bricked devices is something else that most people are blind to. If you recall the first attack on the Ukraine, the bad guys, the Russians, remoted into 30 Ukrainian substations as part of the attack. It was a bigger attack, but the piece I'm focused on is remoted into the substations, erased the hard drives on the computers in those substations, and bricked some serial to TCP converter devices. What does that mean? They downloaded new firmware that was all zeros, and now the devices could not reboot. You go, oh, we need to clean that up, put the proper firmware back on there. Well, you can't. You have to boot the device so that the software can load firmware into the device. If you can't boot the device, you can't load new firmware into it. You got to throw the device out. You got to replace it. Now, with these controllers, these are commodity devices. They do only one thing. They were, I assume, comparatively easy to replace. With our PLCs, it's a different animal. If we have, 50 PLCs in the mine and we need them all, or, in the primary processing site that's part of the mine. And, we might say, I have a 20-year expected life on these devices. I know some of them are going to fail. So I have 10 spares sitting there. And I've got 30 devices deployed. I've got 10 spares that should last me the whole 20 years. And I brick the devices. And now I have to throw them out because I cannot. There's physically no way to load new firmware onto there. All I've got is 10 spares. I need 30. Where am I going to get the other 20? You can't buy them on the, from the vendor anymore. The vendor doesn't sell them anymore. They went out of sale 5 years ago. How am I going to recover this? I've got to buy new PLCs, reprogram them, recertify them, retest them for safety. It's going to take me weeks or months. So these brick devices are an issue that people aren't paying attention to. Worst case scenario, you pivot through the cloud into not just one mine, but 20, and you brick all of a certain kind of a device that's connected to the cloud, and now there isn't inventory of those devices anywhere in the world because, the vendor hasn't built, that many spares. So again, there's blind spots in risk assessments that we need to become more paranoid. This is why engineering teams need to learn about cyber attacks, not just defenses, cyber attacks, so that we can figure out what are we up against here. If every CPU in the mine starts executing, starts giving to the physical process the worst possible instruction that is possible to give to the physical process, what's going to happen? Well, the mine's probably going to shut down. That's probably, an acceptable consequence. Having things blow up, having people die, having equipment crippled so that the mine is down for months, that's an unacceptable consequence. Okay, we need to become more paranoid in applying attack knowledge to our automation systems so that we can figure out what kinds of defenses do we need. Something else that's new in the world, this is my most recent book. It is written from the perspective of CIE. It's not primarily about CIE, but it's saying, take that perspective, cybersecurity on one side, engineering on the other, risk to physical systems, brick devices, take that whole perspective and say, where does that lead us? How it tries to answer the question, how much is enough? How much cybersecurity, how much engineering for which kinds of systems? Because a small shoe factory deserves a different protection than does a large mine. And one of the sections in there that I want to talk about, chapter 5, is network engineering. And this is where we're talking about, look, the preferred way, the usual way that intelligence agencies, that nation states, that ransomware, the hacktivists, the usual way they come after us is through the network. And so if they get into our OT systems, if the consequences are unacceptable, because we have software safety systems, we have software protective relays, if the consequences are unacceptable, we've got to we need engineering grade prevention of the propagation of attack into this consequential network. You don't use network engineering everywhere. You use network engineering at consequence boundaries, at the connection between a business network, where if you compromise it, you have business consequences that you can often buy insurance for, at the connection between that business network and a network, an OT network, an automation network, whose worst case consequences of compromise are unacceptable. At that consequence boundary, at that criticality boundary, that's where we need to prevent pivoting, getting through into the network. How do you do that? There's a number of different ways. I won't go through them all. It's in chapter 5. Let me give you just 2 examples. The simplest example is analog signaling. If I have a bunch of safety instrumented systems, and my operator, the plant operator at the mine, in their SCADA system wants to see the status of the safety systems, how can I do that safely? How can I do that without introducing a pivoting path into the safety systems? Well, safety systems are comparatively simple. They have one job. They have a limited number of outputs. I'm alive. Okay, the operator needs to know if a safety system fails because they need to be replaced promptly. So there's an I'm alive signal, and there's a signal saying, I've tripped. I've tripped or I've not. If I've tripped, I might want an analog signal saying which cause, what reason have I tripped? And there might be 79 reasons. So I send a number between, 1 and 79 saying this is the reason. Those are the outputs. You can signal those outputs through 4 to 20 milliamp current loops. You can signal those outputs through analog signaling. You don't need messaging. Attacks pivot through TCP, messaging, Ethernet, internet protocol. This is how attacks pivot. I defy you to send ransomware through an outbound 4 to 20 milliamp current loop that sends a 1 or a 0. I defy you to send anything back, much less malware. So increasingly, we're seeing people connect their safety systems to their HMIs through these current loops. Now, these current loops, they cost about $500 per endpoint. If you got 5 of them, that's a $2,500 cost. That's entirely acceptable for a safety instrumented system. If you've got 1,000 or 10,000 values, you've got a signal. You can't do this. It becomes impractical. So that is a simple example of network engineering. The most common example, the most widespread engineering out there is unidirectional security gateways. And for the record, this is what Waterfall produces. So, for anyone who's not familiar with the technology, the most common kind of network engineering out there is the unidirectional gateway. The gateway is a combination of hardware and software. The hardware physically is able to send information in only one direction. There's 2 circuit boards. There's a fiber optic transmitter on one. There's a receiver on the other. You can send from one to the other. There is no sender. There's no transmitter in the receiving circuit board. It's not physically possible to send anything back. So that's the hardware, and the software makes copies of stuff. If we have an OPC server in the mine with all of the data in it that our predictive maintenance wants to use, or that our business automation wants to use, if we have an Oracle server, a SQL server, a Pi server, any kind of server that is sort of the focus of IT/OT integration, the unidirectional gateway software logs into that server, usually once a second, but it's configurable, and asks for everything that's new. All of the data since the last time I logged in. With an OPC server, logs in, I don't know, once a second and says, please give me all the tags and all the values. If it's a PLC, log in and say, give me all your registers and all your values. Takes that snapshot of information, might be a megabyte, might be 50 megabytes, pushes it through the strange one-way hardware, and on the outside, inserts the data into an identical system. If it's OPC in the inside, it's OPC in the outside. If it's Pi on the inside, it's Pi on the outside. And now anybody on the outside network here who needs the data asks the copy of the system for the data, and they get the same answer as the live system would have given without ever sending anything back into the industrial network. All of the data that's allowed to be shared with the business is out here on the business network already. So that's the idea. It's a mature technology. I mean, if you lift the lid on these devices, there's a physical divider down the center. This is in fact 2 devices built into the one, the transmitter and the receiver. You can run your finger down that divider. You can prove to yourself that this is engineering grade unidirectionality. It's not physically possible to send any signal back. I mean, think about it. All cyber sabotage is information. If the only way that a control system, any kind of control system, can change from a normal state to a compromised state, the only way is if attack information enters the system. If we reliably prevent information from flowing, we reliably prevent attacks from flowing. We reliably prevent attacks from pivoting. So unidirectional, engineering grade, a ridiculous number of software connectors. If you need to make a copy of OPC, of course we have it. If you need to make a copy of Honeywell PhD, we can do that. If you need to make a copy of, Plant Web Optics from Emerson, we can do that too. There's a ridiculous number of connectors here. This is a mature technology. And, it is a network appliance. I mean, it looks like this. That's what it looks like. What's the user interface? It's a web-based user interface. You use it to configure the device. You use it to manage the device. You use it to troubleshoot the device if you need to. Again, a mature technology. You put it in between the 2 networks and you configure the device. You don't need to install software anywhere else. You configure the device and off you go. Now, let's talk some mining examples. Most mines are remote. We can't build mines in the middle of cities. And so getting out to the mine is 9 times out of 10 a problem. We need remote access. But what we've got is we're asking for remote access to an automation system, most of which is safety critical. Why does it make sense to enable remote access to safety critical systems? That's just hard. Here is an example of the safest kind of remote access. It's called remote screen view. It does require somebody at the mine to help us out. So what happens is someone at the mine sees an error message, says, I need help with this. I need the vendor to come in and help me. Picks up the phone, calls the vendor. The vendor says, great, let me see what you're doing. The engineer turns on remote screen view, and basically a video of their screen start, much like you're seeing a video right now of my screen right here. A video of the screen goes out through the one-way hardware. The vendor can see it. Now, the vendor can move their mouse all they want. Nothing can get back into the site, but the vendor can say, oh, I think I see your problem. Can you bring up the system diagnostics for me? And they can see the mouse moving. And they can say, no, that's communication diagnostics. 2 further down. There you go. That's system diagnostics. They work together to solve the problem. Nothing from the internet, no nation state, no nothing can leak an attack back into the industrial network. It's all coming voice-wise over the phone into the head of the engineer. Now, you do need procedures for the engineer to call the vendor, not vice versa. You do need procedures for the engineer to know who's on the other end of the phone, so that you don't have someone spoofing and saying, ha, let me explain to you how to hack your own system. No. But once you've identified who's on the other end and you've determined that they're trustworthy, you can take advice from them and work with them to solve your problems. Another approach is, look, if we absolutely need two-way remote access from the outside world, here's one way to do it. If we need that kind of remote access, what we need is software security 9 ways to Sunday, every bit of software security we can find, VPNs, encryption, two-factor authentication, jump hosts, firewalls, you name it, put it all in there, and put a secure bypass unit in there. And the secure bypass unit is copper in, copper out. It looks vaguely like a gateway, copper in, copper out, but inside there's electromagnets that are separate. Nothing goes through the unit. You can leave all of your software there. The bad guys cannot be testing your software all day long, looking for a vulnerability. They cannot be probing it. They cannot be trying to take it over because they can't reach it. It's isolated. For the half hour that you need help, you turn a key on the device. The electromagnets connect. Now, for a half hour, you can activate all of that software protection, do your thing, and there's a timer in the device. After half an hour, it separates again. Nothing gets in. So this gives the mine site, physical control over when that software protected remote access is enabled. So those are 2 examples. There's other examples, 2 examples of how to do safer remote access for the mine site. Let's talk about abstraction real quickly. I mentioned the cloud. Increasingly, we're seeing the cloud used in mining and in metals. Concrete example. Let's say we have a materials processing optimization application in the cloud, an AI. Let's say we're operating a strip mine. We've got a shovel goes into the rock face, or there's been we did our explosion. We've got this pile of rock. Shovel comes up, picks up 700 tons of ore, drops it into a truck. The truck drives away to the primary processing site. In the shovel, there are sensors. In the truck, there are sensors. They're sending measurements of that shovel, that load of ore, out into the cloud. The AI is analyzing the measurements, and by the time the truck gets to the primary processing site, the AI has figured out optimal processing instructions so that we use minimal energy, minimal resources, that we process just this load of ore just enough to extract maximum value from it. But those instructions You can send the data out to the cloud through a unidirectional gateway. Nothing can get back. Those instructions have to get back. Well, we can put another gateway oriented inbound for those instructions. Yeah, but what if the cloud is compromised? What if the cloud produces a faulty set of instructions, a set of instructions that is dangerous? Most of our equipment can only be operated in a bunch of safe modes. A rotating drum might have only 2 safe angles. A crusher might have only 3 safe speeds. And if what we send from the cloud into the processing site is 1,000 records, each of which has a timestamp, a PLC name, a register number, and a value. We got 1,000 register numbers and values coming by. Is that a safe configuration for the site, or are we going to damage the equipment, or worse, injure somebody? Well, I would have a hard time looking at a document like that, trying to figure out if it's operating safely. I would have a hard time, and I've written a lot of code in my career. I'd have a hard time writing a program to completely reliably determine that this is a safe configuration. A better way to do it is to use an abstract representation of the instruction coming in. Think of it as an XML file. Let's say the crusher has only 2 safe angles, 17 degrees and 23.5 degrees. Instead of sending 23.5 in, send in an XML file that says crusher angle, and the value is either low or high, LOW or HIGH, closed section. The rotating drum speed, let's say can be anywhere between 3 revolutions per minute to 7 revolutions per minute, anywhere in between, but not below and not above. So send in drum speed, 6%. It can be a value between 0 and 100%. And you send in this abstract. If you send in a document like that, and the only values that the document accepts, that the document can express, that the schema can express, if the only values they can express are safe values, well, now we've got, in a sense, guaranteed safe information coming in. I can look at it and say that makes sense. Low, medium, and high. If I see higher, what do you mean higher? There's no such value. I can visually verify that this is a safe configuration of the equipment. I can write a program to check the document against the schema. Abstraction saves us. Now, it does mean we need an extra step inside the processing system. We need a batch processing system or a manufacturing execution system. We need an extra piece of software to interpret the abstract specification and turn it back into the concrete PLC values. But that safety critical function is happening inside the mine site, behind the network engineering protections. It doesn't matter if we compromise the AI. The worst that can happen is we operate suboptimally. We lose a little money. We can buy insurance for that. Nothing gets damaged. Nobody dies, because the safety critical decisions have been made on the industrial network. So abstraction is, again, a key concept I describe in chapter 5. One more concept, and I'm running a little over time, and this is dependencies. The last couple of years, people have been talking a lot about dependencies. Let's take that same example. Instead of the AI living in the cloud, let's imagine that we've brought it in-house. It lives in our IT network. Ransomware comes in, takes over the whole IT network, cripples everything. What happens? The mine stops, because we can't dump ore into a processing facility that doesn't work. So what we have is the safety critical mining automation system. We have the business critical IT system, and part of that IT system is, in fact, a reliability critical component. The mine relies on that AI. And so what do we do? And again, one of the network engineering principles is, when you look at reliability, you have to look at the minimum or the maximum acceptable downtime. So if ransomware comes in, wipes out our IT network, how long is it going to take to recover? It might take days, it might take weeks. Do we want the mine to be down for weeks? No, we can't afford that. So what we have to do is train our incident response people. We've got to identify beforehand, we've got to identify which parts of the IT system are reliability critical. There's safety critical, there's business critical, and there's reliability critical. Identify the reliability critical parts, put them in their own little network, train the incident responders that when there's an incident, don't start looking at the IT network, go straight to the reliability critical, put them on, I don't know, virtual machines, recover in minutes, have your transaction logs, if they need persistent knowledge, have those transaction logs written to write once media, replay the transactions, bring your last snapshot right up to speed and restart the mine. That means, though, that we've done network engineering for the reliability critical network as well. It means we've identified the dependencies in turn. It does no good to restore the AI if the AI, in fact, needs the Active Directory server to start up. And the Active Directory server is still sitting on the IT network crippled. We need to identify this recursive chain of dependencies and make sure that we can restart the reliability critical components. Make sure we've trained our incident responders to restart those components first, so that our downtime at the mine is an hour, which is acceptable, not 4 weeks, which is unacceptable. So these are all concepts in network engineering. These are all concepts that arise when you look at the problem from an engineering point of view. When we take the engineering lens on risk, on the expectations of protecting public safety, protecting equipment, take those expectations and apply that engineering methodology to the question of cyber attacks on our automation systems. That's what I had for you. Waterfall has been around for 17 years. We have offices all over the world. We have installations all over the world. We are trusted by mines. We are trusted by, power plants. We're trusted by critical infrastructures of all types, by heavy industry of all types, all over the world. That's what I had for you. The book is free. Waterfall sells product, not books, technology, not books. If you'd like a copy, go to the URL, waterfall-security.com/engineering-grade-ot-security. You can see the title there, and you can request a free copy. And I've been talking about engineering. Don't get me wrong. The coin has two sides. We need engineering. We also need cybersecurity. The sites that I work with at Waterfall that use the engineering approach to protecting against cyber threats, the sites that use engineering the most intensely also use cybersecurity the most intensely. They go hand in hand, but I've been focused on the engineering perspective because that's the piece that's been neglected. That's where there's powerful insights and tools that are available to us that we've been neglecting and that can help us along the path very effectively. Jonathan, that's what I had. Do we have questions in the queue?
Yes, we have a few questions from the crowd, some of them from the beginning, some of them from just now. Let's go ahead and get to the questions. So a gentleman named Brian asked it towards the beginning, it seems to me during when you were showing the threat report, he asks, what does it mean by 68 attacks impacting more than 500 sites? And then he just speculates, is it 68 of a specific type of attack? What's the connection between 68 attacks on 500 sites? What's the overlap?
Well, let me give you a concrete example. In 2017, ransomware crippled the IT network at Norsk Hydro. And Norsk had, I don't know, dozens of power plants. They, disconnected those power plants from the IT network and they kept going. They were fine. They had a few, a number of aluminum smelters, okay, because smelting aluminum consumes enormous amounts of power, and Norsk Hydro is all about hydro. It's all about power. If you have access to enormous amounts of power, you have a competitive advantage in smelting aluminum. So they had a lot of aluminum smelters, and they said, we don't trust the automation in these systems as far as we can spit. They turned off all the automation. They operated the smelters manually. So there was no effect on the power plants. They trusted the cybersecurity there. They just kept going. There was no effect on the smelters because they did not trust the automation, but they turned it off and they were able to operate manually and they just kept going. And there were, I think, 4 sheet aluminum plants that were heavily automated, so heavily automated they could not be operated manually anymore. And they did not have robust cybersecurity programs. And so the Norsk Hydro, in their public report, they were very public about this. They reported that they shut down those 4 plants. So when I count sites versus attacks, I count that as one attack. It was one action on the part of the adversary. They compromised the IT network. The consequence was 4 sites went down. So in our report, it's 68 actions on the part of adversaries, 68 attacks that took down 500 sites. Some of the attacks took down 1 site. Some of the attacks took down 24 sites.
Okay, that certainly clears it up and explains the numbers there. We have an anonymous question that someone asked regarding, and this was a little bit later in the webinar. He said, "Would there be any latency if the systems are moved or hosted on the cloud?"
So this, what's the late? So I'm not quite sure I understand the question. There's a couple of questions that I could possibly answer. Let me answer them both. One is, if you put important systems into the cloud, does that increase your latency? The answer is yes, of course. The internet, only runs so fast. The further away, speed of light propagations, light takes 1/7 of a second to run around the planet in a vacuum. Okay, in fiber, it's slower than that. In copper, it's even slower than that. So yeah, your latency increases the further away you get. But so you don't put safety instrumented systems in the cloud. Nobody does that. You need low latency. You need sort of the local trust. You can't do that. The example I gave was one where the truck is on its way. It's going to take 1.5 minutes, 90 seconds to drive from the rock face to the processing plant, and another 60 seconds to unload in that processing plant. In that 2.5 minutes, is there enough time to get the data out to the cloud and get an analysis back? You bet there is. Of course there is. Now, what happens if the internet fails? Well, you're going to need multiply redundant internet connections, because the internet does fail, and we can't afford to shut down the pipeline, or sorry, the refining site, or the processing site. We can't afford to shut down the mine every time the internet fails. That's just silly. So to me, the key question is not latency. This is a decision process that can easily be done in seconds, and we have minutes for it. The question is not latency. The question is the reliability of the internet, and we're going to need multiple fail safes so that cloud-based system is available reliably, so that we can operate the mine reliably. A second question, that might be involved here, I think that was the main question, but the question is also sometimes, if I'm sending stuff through a unidirectional gateway out to the IT network or to the internet, what kind of latency is there? It depends on the connector. It's typically, between 100 and 200 milliseconds. Depends on how busy the system is on the IT network. If we're pushing stuff into an Oracle database, an Oracle database with 1,000 users sometimes slows down. However long it takes, that tends to be the piece of it that drives the latency. But again, when we're talking inside the mine, sometimes we're talking millisecond latencies matter. When we're talking the IT network, again, usually these decisions are made in 1 second or 3. Anything less than 30 seconds is considered real time in terms of human decision processing on the IT network. That's the time frame. 100 milliseconds, nobody notices in the IT network.
Okay, excellent. And then let me see here. We had a few more. I don't know if we'll get a chance to get to all of these. This is a good question here. How likely is an attack on mining safety systems in the next few years?
That's a tricky one. There have been attacks on safety instrumented systems. But, in a sense, it's the wrong question. The word likelihood is a tricky one, and I deal with that in chapter 6. Likelihood works for, let's say I have I have an IT network. I used to work many years ago for Hewlett Packard. At the time, there was 150,000 employees at Hewlett Packard, most of which had a computer on their desktop. So let's say there was 100,000 computers, workstations with people getting email every day and clicking on things. How many times in that 100,000 population of users are you likely to click on a piece of malware? Well, let's say last year it was 73 times. How likely is it to happen next year? Well, we're likely to have, between 70 and 80. We're looking at the trends over the last years. When we're talking high frequency, low impact events, likelihood, frequency, those concepts make sense. If we're talking looking forward at low frequency, high impact events, likelihood isn't something that, it's not a question that makes a lot of sense. What we need to be doing then, I mean, if you look at likelihood, if you look at the risk standards, what is likelihood? It's a combination of opportunity and threat and capability and if you look forward at low frequency, high impact events, it is prudent to defend against widely available attack capabilities. It is unwise to design our defenses against what we think our enemy's intent is. Capabilities change very slowly. Intent literally can change in a heartbeat. And so looking forward, we should not be asking the question about likelihood. I submit the right question is, what are our enemies capable of? And what do we need to do to address those widely available capabilities? Not what do we think is their intent next year? So that, I don't think that's quite the answer you were looking for, but I would focus on defending against widely available capabilities rather than trying to predict next year's intent.
Okay, excellent. We have a whole bunch of more questions that came in towards the end there. For those of you that asked that we don't get to your questions, either Andrew or someone else from Waterfall will get back to try to provide you with an answer. Thank you everyone for joining. Thank you, Andrew, for the excellent presentation. We will be sending you an email with a recording of this. So if you missed anything or if you want to share it with a colleague, that's how to do it, is with the recording. And that wraps up the webinar for today. Thanks, everyone. Have a great day. Thank you, Andrew.
Thank you, Jonathan. Thank you, everyone. And yeah, if there's questions in the queue, I'm on LinkedIn. You can reach me with my email on LinkedIn, Andrew Ginter, Waterfall. I'm happy to answer questions there. And I've got the questions in the queue. I'll try hard to get you folks an answer in the next 24 hours so that you have your questions answered. Thank you, everyone.
Thanks, everyone. Have a good one.